It's a visitor. Okay. Yeah, it's a visitor of wheelchair. It's home because it's infected by COVID. So, and well, Paul was a student of Filippo Sant'Ambrosio, and now is a maître de conférence in the University of Paris, Dauphine, exactly Paris. And he's going to talk about some optimal transport.
Oh. Thank you for the introduction. Thank you, Mirza, for the invitation. I'm very happy to be here. It's been I don't know, for 3 years that we planned this visit, and finally, it's possible. But Mirza, maybe I will meet him sometime. I hope so. So today I will talk about optimal transport, and more specifically entropy-regularized optimal transport. And this is a joint work with Guillaume Carlier, who's a colleague in Dauphine, and Lugar Tamanini was a postdoc with Guillaume at that time. And so the plan of the talk is very simple. So I will do quite a lengthy introduction to optimal transport and to its entropy-regularization, because I was told that not all of you know about optimal transport, so I will spend some time on it. And then we will discuss, so there will be this entropic-regularization of optimal transport, and we will tackle the issue of how fast it converges to the original problem with some parameter, and we will get some upper bounds and some lower bounds. And I will try to explain a little bit the strategies of the proof for the people who know a little bit more the topic. Okay, so let's start with the introduction. So the optimal transport problem is a very old problem. It dates back from the 18th century. So the idea was it was an engineering problem. So you had some distribution of signs, a mu minus at the origin, and you want to send it to another distribution of mass, mu plus, so this mu plus, this mu minus, for example. And you want to do it in the most efficient way. And here you transport the sand through some map T, which we call a transport map. And it tells you if you had some sand at position X at the beginning, you will send all this pile above it to this point, T of X. Okay. And what you impose, you want to minimize some cost by doing this, but you want to send the global distribution mu minus here to mu plus. Okay. And in modern language, it can be written in this way. So you have a cost C. Imagine in the original problem of Monge, it was just the Euclidean distance. So X is the source point, Y is the destination. And here, take for example, C of XY is the Euclidean distance from point to point Y. And the heuristics in this is what you pay is the mass times the displacement. Okay? And so the cost is this, so the integral of the cost for moving from X to T of X against the mass that is moved this way. And the constraint is a push forward condition. Okay, so it means that if you push mu minus with the map T, it gives a mu plus. So this so you have this push forward operator. Maybe I should just now so T push forward mu minus of some set, let's say E is equal to mu minus 1 mu minus of T minus 1. Basically, I've drawn a little picture here. What does it mean, this push-forward condition? Is just if you take a vowel set B here in the target space, you look at all the points that were set to B, so T minus 1 of B, and you are just saying that, okay, the area above here should correspond to the area above. Okay, so the drawback of this formulation is that you see it's highly nonlinear. If you have some cost C which has no particular structure, the cost here is linear, but the constraint is even worse. So this form of operator is not this is not a linear constraint. So from a functional point of view, this is very bad to get existence, for example. Okay. So the idea of Convergence was to relax this problem and so to allow more general movements of mass. So now a particle at X, well, it doesn't have an assigned destination, T of X, but it can have several of them. some several destination y, and this would be measured through some measure gamma here, which is on the product space, okay, x minus times x plus. And it tells you, so the product of the position of the sources times position of the destinations. And gamma of some dx dy tells you how much mass which go from dx to dy. Okay? And now the formation is this one. So you minimize the integral of the cost moving from x to y against the mass that you move. Okay? And the condition that gamma says mu minus to mu plus is saying that it is a transport plan, gamma is a transport plan. So its first marginal is mu minus, and its second marginal is mu plus. What does it mean? It means that if you take gamma and you project it on the first component, on the mass, well, you should recover mu minus, and you push the mass of gamma to all the destination points, to the second component, you should get mu plus. Okay. And now this is very nice because you can see it's a linear problem. So this is a linear functional in gamma, you see. And this constraint, it's a Dauphine constraint. In particular, it's a complex constraint, which is really fall in the category of linear programming problems. But here also infinite dimension. Okay. But anyway, this with this you can get existence almost for free under very general hypotheses. For example, when C is over some hypotenuse, and the measures are compact support. You also have existence of a dual problem, like a convex optimization problem, okay, and many interesting properties. Okay, I will write here the dual problem because we use it several times during the talk. So, it's a dual problem in the sense of the convex duality. And here you can see you have two types of constraints. The first constraint on the first marginal, and another constraint on the second marginal. So you get two Lagrange multipliers in the dual. Okay, and they live in some dual space. Okay, so it's not really the dual, but the pre-dual. So the measures are the dual of continuous functions. So the Lagrange multiplier would be continuous functions. Phi for the mu minus constraint and psi for the mu plus constraint. And the dual functional is this one. Okay, with some constraints here, which is phi plus psi less than 6. So let me just say what is phi plus psi. Phi. There are some Martes. So phi plus psi on xy is just phi of x plus psi of y. And so this is a pointwise constraint. Okay, for every x and y, phi of x plus psi of y is okay, and the control duality, which is a particular instance of convex duality, tells you that okay, there is no duality gap. So this infimum is equal to this superior. Let me just say another thing that okay, it's really a relaxation of the original Munch problem that we have seen just before. Because if you have a Munch candidate, so a transport map from mu minus to mu plus, well, it uses a transport plan by this map. So you see here it's a graph map, and you push forward mu minus to the graph map. So it gives you a measure of the product space. If you have some visibility, okay, and you have some measure here, distribution mu minus, and the measure gamma t here will be supported on the graph of this function. So the graph of x gamma t is just push forward. So just to be able to push forward mu minus. So if you want to measure what's in this box, you look at all the points lying in the graph. Okay, you look at which axis it corresponds to, which is mu minus of this. Okay, so it gives you a measure of the product space, which is very sparse. It's concentrated on a graph in this case, and we call this transport plan deterministic. Okay, and once you do this, okay, you can check that it's admissible, so it satisfies the. Maybe this here is better. You can see this gamma t is satisfies the constraint by mu minus mu plus, and the cost is the same. Okay, if you take the Munch cost of t, it corresponds to the Convergence cost of this gamma t. And you can show that it's so you can embed the transport map in the space of transport plans, and you take the lower semi-continuous envelope, you get exactly this problem. So it's really a relaxation. Okay. Right. Let me just keep something. Okay, so I just want to stress some important features of the theory of optimal transport that we will use during the talk. So it's basic, what you learn maybe in the first courses of optimal transport, but just what we need in the okay, so I recall the duality. The if of the primal problem is the soup of the dual problem. You have existence for almost for free in several instances of solutions for these two problems. And for the dual problem, actually, once you have optimizers, you can take them in a very special way. You can take them to be C conjugates in this sense. So once you have a psi, you can define this function of x, inf of C of xy minus psi of y. This is called the C transform of psi. And you can do the similar in the y variable. This is called the C transform phi. And you can assume that phi is the C transform of psi, and psi is the C transform of phi. Why? Because okay, you see, you want to maximize these two quantities. Okay, this sum here. Here you have a constraint. So the constraint is phi of x. Phi of x should be less than, I'm putting the psi on the other side. C of x y minus psi of y. And this should go for this x, this should go for every y. Okay? And you want to maximize the phi. So you want to get the maximal lower bound for this. This is exactly the issue. Okay? And you think that okay, you can always replace with this, and once you iterate it twice, you fall back. So you can have that both are sequential. Okay. Now, once you have convergence potentials, convergence potentials, I mean solution of this of the dual problem, which are sequential. Okay. Then you have a simple way to characterize optimality of the primal problem. Okay. Gamma is optimal in the primal problem if and only if its support is included into this the contact set. So I recall C, this quantity here, it's always non-negative, so we write it as E of xy. It's an energy which is always non-negative. And the gamma is optimal if only the support lies exactly on the zero set when you have contact. Okay, you can show it's not complicated. Okay. And finally, if C is twisted, so you have some injectivity of the gradient of C. We'll see an example just later. So there is this condition. Then there is a unique optimal plan. So this solution is a unique problem, and it's deterministic. So it's meaning that it's exactly of this form. So it's marginal in this case. The most famous case is the quadratic cost, for example. Okay, so it's the square Euclidean distance. It's the most used in the literature. Okay, and you can compute the gradient of this quantity. It's exactly x minus y, and it's ejected in that case. So it falls in this twisted category. So it's just the generalization of this. Okay. So in this case, you can say more things. You can actually say that when u minus is absolutely continuous, then the optimal transport problem is a unique solution. And it's induced by some map. And this map is very special. It's a gradient of a convex function. This is from the famous Brené theorem in the 90s. It's the gradient of a convex function, and it's the only gradient of a convex function that sends u minus to us. So this is a very special case. And the proof of this is obtained exactly following these steps. So then once you have this, okay, you just write the optimality condition and it's also. Okay, and in this case, you have a very nice metric that is induced in this case. Okay, so the optimal cost given u minus and u plus, it's called the two varepsilon distance. So it's a non-negative quantity, which is a metric. So it's a distance over probability measures. It measurizes the weak convergence of probability measures, and you have many nice geometric properties there. You know that it's the geodesic space. It has some kind of Riemannian-like structure. You have a theory of Wasserstein gradient flows. And you recover some PDs and some certain gradient flows for this metric and so on. So it's widely popular for this. And it's used in many different areas also, statistics and machine learning. So as a data fidelity term, for example, in fluid mechanics, economics, physics, and so on. So now it's becoming more or less a tool that is used in many other problems. Okay, and you have part of the success of this is also that now you have some efficient methods to compute approximate solutions of this transport problem. So you have the basic method, network simplex, optional algorithm, semi-discrete methods, which corresponds to one measure is atomic and the other is absolutely continuous, Monge-Ampère solver, and so on and so on. And the one that we will be interested here, which is more related to the talk, is the Sinkhorn algorithm, which is related to the entropic regularization that I will define just in an instant. Okay, so Sinkhorn algorithm is just like a block coordinate ascent with the regularized optimal transport problem, which is this one. Okay, so the entropy-regularized problem is you take the fact that we had before. So if you just have this term, it's the classical optimal transport problem, and you add a penalization term. Okay, it's epsilon times the entropy of gamma with respect to, and here it's the product of the marginals, minus plus. Okay, epsilon is a small noise parameter, and this entropy is the Boltzmann channel non-relative entropy. So basically, if gamma has a density rho with respect to p, it's just the integral of rho of rho, and you set it to plus infinity if it's not the case. In this way, it's a lower semi-continuous functional. This term forces the gamma to have a density to minus n plus and not to concentrate. Okay, so when epsilon equals 0, it's the classical optimal transport problem. But now, when epsilon is strictly positive, you see that this is a strictly convex function. So here it's a strictly convex function. And this is interesting. Why? Because then you know that you have a unique solution, gamma epsilon. While in the classical case, epsilon equals 0, in the original case, it was a linear problem, and in some instances, you have several solutions. Solutions that you may have solutions that have finite entropy, you may have solutions that have infinite entropy, maybe all have infinite entropy, everything can happen. For example, in the Munch case, for just Euclidean distance, it may happen that you have two solutions, that something which is really absolutely continuous with respect to the base of the product space, and something which is deterministic. The two can be solutions. Okay, but for epsilon simplicity, there is a unique solution. So this is an advantage of this. Oh, okay. So just wait a second because my laptop is going to shut down if I don't do something. Okay. It's a little bit. Maybe my. Okay. This is a little bit. This connector is a little bit broken. So okay, this way. Usually for the seminar, I use this computer. I've always managed to use it. So that's a bit worse. Okay. Okay, so this is the entropy-regularized problem. And for example, what does it do when you consider absolutely continuous measures, marginals? And in the situation, for example, in the quadratic case, when you have a unique solution which is concentrated on the graph, the gamma epsilon are some kind of blurred version of it. Okay, so this is, for example, so it is from the book by Coutury and Perret on computational optimal transport. This illustration, very nice. Here, for example, it could be for epsilon very large, so you get something which is almost b minus times b plus, and you decrease epsilon, decrease the temperature parameter, and you will see that you will converge to some to the optimal transport map of the limit. So this has a blurred version which converges to the deterministic solution. Okay, and similarly to the original optimal transport problem, since it's no more linear, it's still convex problem. So you also have a dual problem for this. And here about the dual, okay, you recognize the term that we had before, integral of phi d minus plus integral of psi d plus. And you have this strange term, okay, which is a little bit weird, but we can write it in a different way. So this is an expression that we call it log sum x expression, the log, an integral, and an expression, log sum x. And actually, when epsilon tends to 0, this converges to the minimum of this function inside of c minus phi plus psi. So it's some kind of epsilon regularization of the minimum operator. So we call it a soft minimum operator. It's you can relate it to the original problem. You can write the original problem as you have a constraint on c minus phi plus psi, and you can also write it in this way of plus minus the minimum of c minus phi. So it's really you can recognize the original problem on this. Okay, where does it come from? Where does this matter? Well, as I said, it was introduced for the computational purpose by Título. We introduced the Sinkhorn algorithm for solving quantity problems. So once you have this regularized problem, you have a very fast algorithm to compute solutions. Okay, it's called the Sinkhorn algorithm, and it corresponds to doing just a block coordinate set to the dual that I just wrote before. So you maximize with respect to phi, there is a closed form formula on this. You maximize with respect to psi, and then you iterate. And it's really like a two-line, the simplest way to implement it. Then you have speed ups, you can speed this thing up. So it's very simple and it's very fast. Okay, but you don't get the original solution, you get only approximate solution because of this parameter of psi. So it was discovered and implemented many times in different contexts. It's also called IPFP, RAS method. You can see it everywhere, basically. This is related also to the Schrödinger bridge problem, which is a probabilistic problem. You can see the work of Leonard for the quadratic cost. You have the first proof of convergence also. The problems as epsilon equals to 0 in this work. But on this, I'm not very competent. Just to say you have a connection with this problem. So it. And now this is why we use the optimal transport to approximate the optimal cost, the couplings, so the optimal plan, the dual potentials, so Wasserstein barycenters, multi-marginality, Wasserstein manifolds. You have entropic versions of all these, and you can devise the variants of the Sinkhorn algorithm very easily. You get fast algorithms to solve approximately the optimal transport problem. Okay, and what I'm interested in for this problem is the asymptotics as epsilon goes to 0 of the cost, the plan, the optimal plan, and also the Schrödinger potentials, so the solution of the dual problem once you have regularized it. Okay. So, as I said, because numerically this is what you do, you take small epsilon, you compute, and you say, okay, I approximate the original problem. Okay, and but at which phase? Okay, and the first remark that we can do is, okay, just to mention, among these three problems, I will only tackle the first one, which is the simplest one, the optimal cost, the value of the optimal cost, and not the minimizers themselves. Because, okay, our original the goal was to study the convergence of the entropic plan in some in some cases where you don't necessarily have the original optimal transport problem without regularization, and you don't have uniqueness of the transport. Which one does it select? This was the question that we had. But so we didn't manage to do it. But the cost that we had to consider, we noticed that actually even the asymptotics for the optimal cost was wrong. So we studied this. And it has some applications also. So first remark is that it depends heavily on the cost. For example, if the cost, and on the marginal also. For example, if the cost is in separable form, f of x plus g of y, and you can see that actually the OT epsilon is constant, equal to OT0 all the time. Because if you recall this, C of x y d gamma here is just f of x plus psi of y d gamma, but since you have the marginal constraint, this is just f d nu plus psi plus g d nu, so it's constant. And you take just the quantity which is gamma equal to nu minus times nu plus. This is 0. And so okay, this is constant. Okay, but when C is twisted, for example, in the quadratic case, in the quadratic for the quadratic cost, and the marginals are continuous, you know that the solutions are deterministic. They are in this form. Okay, and so with respect to the Lugar measure on the product space, this is this entropy is plus infinity in this case. Okay, so you cannot have the OT epsilon minus OT 0, it must go to 0, but at a much slower rate than epsilon. And the question is at which rate is it going to 0? So what is known in the literature? So you have the non-quantitative results, so gamma convergence and regularization principles, which are known. Okay. I'm citing some people because I haven't been with the people. So the work of Leonard, Adams, yeah, I think. Carlier Duval for also the static formation for Brownian flows. So you have results, very precise results in a discrete case, which actually follows from much older works from Convergence and Martes, which is the general results on linear programming problems and anybody's generalization. In the semi-discrete case, you have results by Lugar, and in the purely absolutely continuous case, you have some theorems on where you have an epsilon, log epsilon, and epsilon terms. So these two first terms and this. But here it's a very strong assumption on the regularity of your cost and convexity, and also the potentials, the convergence potentials. So the optimizers in the original dual problem. And it's a very strong assumption because for to be able to say something about this, you have to use the Carlier's regularized theory, optimal transport, and so on. So really, these assumptions do not come from. And of course, they cover the quadratic cost case. Okay, they're also the result of problem. And then you have second order expansion, so going to epsilon squared, but all for the quadratic cost. Okay, and so the direction of our work was to work in another direction that was what was done before, to assume less things, but at the cost of saying less things. Okay, so we would want low order asymptotics, but under general conditions of the cost and the marginals, and without assuming anything on the optimal transport plans or on the optimal convergence potentials. So we would just for general assumption of the cost and the marginals, and to be able to say something about it. And this is one of the theorems that we have. So if you have measures which are infinity, okay, infinity densities, compactly supported, the cost is C2 and non-degenerate. Non-degenerate is this mixed derivative of the mixed relation, the invertible for the x and y. I will explain a little bit this later. Then you have this asymptotic expansion. So T epsilon is T0. Then you have this epsilon over epsilon term. And in front of it, you have the dimension bit by t. So we will see where this d and where this 2 come from. Here d is the real space, but can be something else. And the remaining is the big O. Okay, as an application, you can say something on Sinkhorn divergences. So what are Sinkhorn divergences? So I said that the optimal transport cost, the original optimal transport cost is finally equals 0. For example, in the quadratic case, is a distance, which is the convergence and so on. But once you regularize it, once you introduce this epsilon, this quantity is no more metric. For example, if you minus equal to plus, it's no more 0 necessarily. And so this Randas and Teddy have introduced this so-called convergence. So it's a correction to this, okay, to make it again a metric. Okay, and actually they show that it converges much faster to the original OT0. And from our results, you can just say that okay, all these terms they cancel, and you just get the over epsilon in these cases. Okay. So maybe I will skip how much time just started.
How many minutes?
How much? 20 minutes. Okay, so I will maybe just say just a few words on this. So just to say that the OT epsilon, when epsilon is strictly positive, well, everything is very nice. It's analytic, actually. So this OT epsilon, the function of epsilon, is analytic on 0 plus infinity. It's a continuous function on the whole plus non-decreasing and concave. This you can show. It's not complicated. It's known as folklore and ability. You have a nice proof using the implicit function theorem. And so that's what the really important thing is when epsilon is to 0. Okay. And this behavior as a degree of epsilon actually corresponds to having a derivative at 0, which is very special and almost never happens except in the discrete or semi-discrete cases. Okay. And this is equivalent to saying that you have an optimal plan for the original problem with 0 temperature, which has finite entropy, which is, for example, in all these cases when you are constituting a graph, this is not true. Okay. And so the question is, okay, if we don't have this rate, what is rate? This is what we are going to do, and we are going to represent you the two separate results, the 3 results. We'll see some upper bounds, some bounding from T epsilon minus T0 from above, and then from below, in a different set of assumptions. And then we maybe give you some ideas of the truth, because it's not so complicated, maybe you can use them in another context. So let's start with the simplest case, when you only assume that you have Lipschitz costs. So the measures are compactly supported in marginals, and you suppose that you have a cost C, which is Lipschitz. Okay? And the goal is to get an upper bound of this form. So this little O will become a big O epsilon. Okay, that you want to say that it's less than a constant times epsilon over log of 1 over epsilon plus a remaining term. And the idea, well, we are going to use the two formulations of our problem. The primal formulation is one formulation. The primal will be good to get upper bounds because it's an infinity. So once you get a competitor, okay, and less than this competitor. And for the lower one, it's the converse. So you can get the lower bounds. So for the upper bound, we use the primal problem, which are recorded here. And it's not complicated. We take as competitor, we start from gamma 0, which is the optimal plan for the 0 temperature problem. And of course, in some cases, you can it doesn't work as a nice competitor because this could be plus infinity in many cases. But we regularize it a bit using a block approximation to explain it in an instant. This is a technique that was introduced by Carlier, Lugar, and so on in 2017 when they studied the gamma convergence of the cost. Okay. And kappa, this constant kappa, it will be a dimensional constant related to mu plus and mu minus. And this is really funny. It's some dimension which is suited to this entropic regularization case. It's the so-called Rayleigh dimension, or also information dimension, entropy dimension. There are also other names, so it pops up in many contexts also. So what is this dimension? Well, it starts this way. You consider a measure mu, and you let's say an RD, and you look at all the ways to partition RD into subsets AN, countable Borel subsets of diameter less than delta. So we call it a delta partition. And you look at this sum of mu of AN log of 1 over mu of AN, and you infimize over it. And then the behaviors of this quantity H delta go to 0, where you can decompose the dimension of the dimension in some sense. For example, mu minus is let's say HK, the k dimensional result measure versus M, which is a compact. Okay, we have probability measures, so I will normalize it. Okay. In this way, you can take AN to be almost both. Okay. Both of reduced delta at some points Excel. Okay, so we do not exactly both because you want to partition, say it's including both containing some both stuff. And so that so mu of the delta of Excel is approximately so C delta to K, K is dimension. And once you do this, you can check and see that
sorry, sorry, could you bring your camera a bit down so we can see in the online?
Yeah.
Okay, perfect.
This you can see or not? Or lower?
A little bit more.
This way?
Thanks. Okay.
Now we do one of the AM. Here, this quantity is almost comparable to yes, exactly. So it's K log of 1 over delta. Okay, so it's almost constant, and when you sum over mu of AM, because you have a quality measure, this is equal to 1. Okay, and so you cover K log of 1 over delta and K is the dimension. So when you divide by log of 1 over delta, you should have solution of dimension, which are up, lower, and upper many dimension. And you can compare it to some well-known other dimension, lower other dimension, Minkowski content of the support, and so on. Okay, and so the proposition is this. OT epsilon is controlled by OT0 plus this epsilon over epsilon. And in front of it, the dimensional concept is the minimum of this upper many dimension. The minimum of the two plus a little o, and you can precise this little o as a big O of epsilon when you say your measures are concentrated in this case. Okay, and the idea, as I said, is very simple. You start with some gamma 0 optimal for T0, and you do a constant by block approximation of this. And you take a countable meta partition, and you replace. So you will have these blocks AI times AJ, and on each block you replace your measure gamma 0 by something which is you see absolutely continuous with respect to product marginals, and which has the same mass, total mass gamma 0 AI times AJ. You do this, and okay, it still satisfies the constraints, and it's close to the original gamma in the infinity Basser set, so some kind of infinity time distance. Okay? Because just to replace the blocks, just need to change a little bit to measure on blocks of size delta. Okay? So it's delta close to the original. Now you plug this into the final problem. And forget the orange part for now, just it's exactly C gamma delta plus epsilon the entropy. And then I subtract and add, because I can, this gamma 0. And this term gives you T0, and you have the remainder term here, and epsilon entropy. And you just want to control the two terms. The first term is easy, because C is Lipschitz, and these two are delta close, so you can just bound by the Lipschitz constant and delta in this case. And now we want to control this entropy term, and you can do explicit computation. And then you have some bounds at the end, but since they are constant, these densities, gamma delta is constant by part densities, you just do your integral, you just decompose it with respect to these blocks. You get the density here, so it's a log of the density d gamma delta, the entropy. And then you split what's in the log into two parts. So you get, we take this mu plus and put it aside. Okay, so the remaining is gamma 0 divided by mu minus, but this is less than this because gamma 0 is a transfer point, so its first marginal is mu minus. So this is just a part of the mass of input. So this is a negative, this is less than 1, sorry. This is negative, and you can forget about this. Just look at this. And using again the marginal constraints, you see that summing over I gives you mu plus aj. Exactly because gamma delta is the right marginal. And you can see this is exactly the sum of mu plus log over mu plus. This is the quantity that we have defined in this okay. So you get this part. Epsilon, this h delta, whatever. And so this is the boundary effect. And you divide by over 1 epsilon, you make epsilon to 0, and you get the boundary exactly that you obtain, which was this one. And I just wanted to say that, okay, here I use mu plus, but of course, you can use the mu plus and mu minus, so you get the mu. I chose to isolate mu plus without any value. Okay, so you can improve this upper bound when you have more information. Why do we do this? Because in the quadratic case, the asymptotic is not known to order 2. In the first term, epsilon was not a d in front of it, it was a d over 2. So, okay, why you only get d and not a d over 2? And actually, you get an improvement of d over 2, but in the first observation, it was 0 1 plus, which is the case of the quadratic. So here we also have some assumptions on plus and minus, because before they were just general measures, now they are infinity, and you can get these improvements. Okay. Just say a few words about this, you get this. You start in the same way by the block approximation, and what you want to do is improve this term, and you can rewrite it in this way. So it's just using the optimality of gamma and the fact that you are you have transport plan from minus to plus, you can rewrite this term in this way. Integral of E d gamma delta minus gamma 0, and E is the duality gap. You see, it was C minus 5 plus psi, when phi psi are optimal. This is a non-negative quantity. It's called the energy gap. Okay, and this is just the integral of the energy gap against the difference between gamma delta and gamma 0. And what we expect that it's actually not in delta, but in delta square. Because at the beginning of the talk, I told you that when you are optimal, it was even sufficient equivalent condition. When you are optimal, you are in the 0 set of the energy, but the energy is positive, is non-negative. So actually, you are in the argument of the energy. So you are going to minimize it. And if E is C2, okay, the gradient vanishes because you are minimizer, and you just get the Taylor expansion, you go to the order. So it's in delta square, because gamma delta is the delta perturbation of gamma 0. So it will be in delta square. Of course, this would be too bit full, so it will be too bit full this way, because okay, even if C is C11, so C2 or C11 is always the same. But phi and psi, you don't know the reality of it. So we have to do something else. And here the idea is to notice that actually phi and psi are C concave. They are almost the same regularity of concave convex functions. And you can use a variant of Alexandrov theorem to still say that you have this delta square. Okay, which should be very rough. Okay, and this power 2, okay, is enough to get this factor 1. Now for the lower bound, you have to use different assumptions. We introduce this non-degenerate condition, which is it was already used this condition by McCann and Pass in their work on the rectifiability of optimal transport plans. And it was also deformed in the Matroun-Norman theory. So it had the mixed derivative. So you take the derivative with respect to y and the derivative with respect to x. So matrix, the square matrix, you assume that it's invertible. It's a little bit like the twist condition, but not exactly. It's like an infinitesimal twist condition, because you just don't ask that gradient x of c is invertible with respect to y. You say that its linearization is invertible. And it allows situations where the optimal you have the solution of the original optimal transfer problem are not deterministic. Okay, so it's a little bit it still has some generality. And yeah, so the point is to get the lower bound of this form. Okay, so same as the upper bound with minus epsilon. For this, as I said, we use the dual problem. Okay. And we just use as a competitor in the dual problem. The solution, the optimal solution in the problem is the 0 temperature. can pick the 5 sides which are conservation potential. In this case, this is exactly OT0. And what you get is this term. OT epsilon is bigger than OT0 minus, this is a soft mean of this, the gap energy. And what we want to say is that this is big enough, so that is small enough, so that this actually is you can see that it's the lowest. Well, at the and you want to say that P is quite dark, so it detaches sufficiently far from 0 when you go away from the contact set. Okay. And to do this, we use a trick of Minty. Minty's trick tells you that this is a funny result. It's really funny. When you look at an increasing, it has a generalization in R. In the 1D case, when you look at an increasing function, if you rotate your head a little bit by pi over 4, okay, then it actually becomes the graph of the one Lipschitz function. That's the exercise. And so this trick was used in particular by Pegon, Pass, and Warren to show that under this non-degeneracy condition, the contact set is derectifiable. In particular, the optimal line, which live on this contact set, they are derectifiable. And actually, so when you see this, okay, I'm saying the contact set is actually graph. I'm saying nothing about what is the energy outside of this set. I want to say that it grows quite fast, and this quadratic, that it detaches quadratic. And actually, you can just reuse their computation and push them a little bit further in a nice way. And to say that, okay, you have some along the graph, energy is constant, so at each point, you have some direction where you grow quadratically. Like a power 2 function. Okay, and this is quite easy. Quite easy. Can be defined when you take, for example, C equals to minus x scalar y. Let me just remove this. X scalar y. So in here the C transforms are just Legend transform. Okay, the conventional function and Legend transform. And when C is a bit general, actually the rotated chart that you want to use, it changes at every point. And still make the computation work. And what you do nicely is something like this. So U and V will be new set of coordinates for the point X. Okay, so X is in RD. In RD times RD, sorry, bold X is the couple XY. Bold X is the couple XY. So it's the 2 points of RD times RD. And U and V are new coordinates, so I'll put it in gray, just affine changes. Okay, and you can bound some of the energies from below by the increment of U, so the difference between the U coordinates squared minus the difference between the V coordinates squared. And for example, if you place yourself on the contact set, so when this vanish, forget about this remaining terms. You just get that delta U squared is less than delta V squared. Delta U squared is less than delta V squared. So U is a function of V. And this is just the proof of that you are in this graph. You have a Lipschitz function constant here, which is almost 1. Okay. But it tells you more, because if you consider, for example, the point X, which is the contact set, so this is 0, okay, and you consider points which have the same V components, delta V 0, but you left the V component which is you want, you get this lower bound, P of X prime is bigger, like let's say almost 1, U prime minus U squared, and you detach it quadratically in the U coordinates. Just very, very easy. And you just plug this estimate into this integral. Okay, you have a little bit of a covering argument, but it's not complicated. So the energy becomes like a minus quadratic squared divided by 4 epsilon. So you get a gross integral, which is of the form epsilon to the 0 over 2. And you get exactly because you are in dimension D in this case. So it's you are getting epsilon, you have a square here, so it's square root of epsilon to the D, epsilon D over 2. And when you pass to the log, you get exactly D over 2 epsilon. So in this case, you can conclude this. And so a quick summary of the results. So you have two types of normal depending on the regularity of solution that you put on equals C. So you have more general upper bound with the non-general solution, and here you have final bound and final solution. And lower bound, you have this non-degeneracy condition. And once you put all these assumptions together, you get exactly the correct asymptotics. OT epsilon is OT0 plus this term plus a below epsilon. And as I said, you recover that the rate of convergence of Sinkhorn divergences and at least the legal epsilon in all these situations. And the perspectives are now, okay, what we had in mind at the beginning was to say something in the limit gamma epsilon, when at the beginning you don't know that you are a single optimal plan. What can we say? Of course, the big O epsilon is still big O epsilon is not precise. We want to do an expression for it in the general case. This is known in the quadratic phase, that's in the marginal post C. And then attack the quantitative base of the potentials of big gamma epsilon also. And this is the rest of the program. Okay, thank you for your attention.
Thank you very much for the nice stuff. So there are already some questions. No, there are. So maybe we start with the people here in the room. So are there some questions here?
Yes.
So, in the case that the optimum transport problem has a unique solution, you know that the limit of this gamma epsilon will be.
Yes. Because of the subsequence in Convergence, and you have a unique limit.
Now, in the case that the optimal transport problem doesn't have a unique solution, in the finite dimensional case, it converges to like self or that minimizes the penalty term that you are considering. Right?
For the fully discrete case,
yeah.
Yes, in this case it is known.
And which is basically among the multiple minimizers, the ones that minimize the penalty.
Exactly, minimizing
the entropy. So are you expecting the same thing here? Or?
Yeah, actually, well, the conjecture in line is that it should be the most spread normal solution. But here, it's possible that you don't have at the limit, you make all the optimal plans, they will have ultimate entropy. It's very possible. I think so it should minimize some relative entropy, but you should have to what measure, not the product measure, something else. And this is we have some ideas about it, but yeah, this is the plan.
Also, in the fully discrete case, you have you also have they also study what happens when you don't fully solve the optimal transport sub epsilon, but you close enough.
Okay.
And then you change the epsilon, like you're doing.
Yeah, it's translating strategies. You decrease the epsilon and
you decrease the epsilon and you're not reaching the minimum.
Yeah.
You're not reaching gamma epsilon, but some approximation gamma epsilon. And there are some gain there that you still make them.
No, I don't have any idea about this, but I think Bernard Spencer worked on this.
Sorry?
Then I think Bernard Spencer worked on something like this. So.
I mean, it's from community.
Yeah, but I mean in the context, in the community.
I'm talking about the students.
Yeah, but not the sudden solution. Spencer is the continuous case or the semi-discrete case or the non-cylinder.
I think they go from the discrete and the continuous. I mean, the full, I mean, basically, when you reduce the finite.
Okay. Then I do. I must say that it's my first, I mean, I come originally from branch transport, which is the line to the water. And this is my entry point in this topic of
Any more questions? We check whether Fecha or Chuaqui have some questions.
Do you have questions? online or no?
It seems that no, unless no, it seems that we don't have questions. No, so thank you. No, I don't have any question, and I think Joaquin also doesn't have, because he's not unmuting himself or.
Okay, no problem. I don't think
Maybe I can ask you a question about the brace slide. What about this
about what?
the lower bound and upper bounds that you get?
Yeah.
So they don't match, right? I mean, at least in this zero. When
So
you assume less regularity, it's zero one.
In these cases they match, okay, but this upper bound, this case, no, they do not match.
But do you think that the upper bound can be improved, or is
No,
the
no.
lower bound the one that?
No, actually, this is sharp. In this class of C01 box, this is sharp.
That is sharp. Okay.
So you take, for example, C to be just the Pegon one distance between the two. U plus equal to U minus, let's say, to do with respect to the leg, and you get this. So you get this is both are sharp in their own kind of activities.
Okay. It's just a lower bound.
And on this general, yeah, and on this general for the other one, we don't know what to substitute. Yeah, and without this non-general condition, for example, you could ask yourself, maybe it's not completely invertible, but you have something on the rank or on the signature of your second derivative here. What can you say? Maybe you can say something replace BD or something. There are some works, multi-marginal transformed by random pass. When you use this as a signature condition, be able to say something on the dimension of the multiply. And maybe this could be extended to this context by replacing this D by signature type condition.
Okay. Thank you once again for this.
Thank you.